all to session 5 of the chapter linear momentum. In this session, we will be learning about conservation of linear momentum, but in case of variable mass. Till now, we considered mass to be constant and we studied law of conservation of linear momentum. In this session, we will be varying the mass and discussing about the law of conservation of linear momentum. Okay. To understand this concept, variable mass system we need to consider. Okay, let me consider a rocket as a variable mass system, right? Okay, as the rocket propagates, right, there will be loss in mass in that, right? Considering that, let us understand about conservation of linear momentum in case of variable mass. Okay, what is rocket? A rocket is a device. A rocket is a device used to place satellites. It is a device used to place satellite in an orbit, right? You need to place satellites in the orbit, you need to send through the rockets. So rocket is a vehicle or the device used to place satellites in an orbit. Rocket propulsion depends on the movement of the rocket. Rocket propulsion depends on law of conservation of linear momentum. Law of conservation of linear momentum. So what is the principle of the rocket? The principle of the rocket is law of conservation of linear momentum, and we will be learning in detail how actually the rocket propagates here, right? So we will be studying about rocket propulsion considering the law of conservation of linear momentum, right? So this session will be on variable mass system, right, taking the example of a rocket. Okay, before understanding how actually the rocket moves, let us solve one multiple choice question, right? So this question itself will give the idea about the propagation of a rocket here, right? The propulsion of the rocket depends upon law of conservation of linear momentum, right? Okay, what is the question? Let's check it out. A person is standing on a frictionless horizontal surface, right? There is a frictionless horizontal surface and a person is standing on that, right? There is no friction on the surface, right? How can he move by a certain distance on his ground? Okay, he wants to move on the ground. How he can move, right? There are four options, right? The first option is by running, right? If he runs, he moves on the surface. Can he run on the frictionless surface? No, the condition is it is frictionless ground, right? So for running you need friction, right? He cannot run because the surface do not provide friction to him, right? If you want to walk, right, if you put the force in the backward direction, you move forward now here, right? So you need friction for walking, running, everything, right? He cannot run because the surface is frictionless surface. Okay, second one, by jumping, yes, no. Let us check it out now here. If I am considering about the jumping case, right, if a person wants to jump, again he needs friction, but the surface is frictionless. So this is also not the answer, right? Running, no, he cannot run. He cannot jump also. By rolling, no, he cannot roll because for rolling also you need a rolling friction now here, right? Without the friction a person cannot roll. So what is the answer now here? By sneezing, right? If he sneezes, right, he will move on the surface, right? Or by spitting now here, right? Let me call now here. By spitting, right? If he is standing on a horizontal surface, if he spits out, right, he moves backwards. Means if he spits, right, the person moves in the backward direction. Means he is losing some mass from him and he is moving. The same thing happens in case of rockets. Rocket will spit something so that it can move now here, right? So it moves in the direction opposite of the spitting now here, right? Okay, let me take a rocket now here. See, if I am considering this is a rocket, right, it spits mass and it moves in the forward direction. So here the same concept we can apply for the rocket also. Means if it loses mass during the motion, it moves in the forward direction. How does it happen? Let us understand here, right? Rockets are of two types. One is single stage rocket and the one is multi-stage rocket. We will be studying both in detail. Okay, let me begin with the first one, that is single stage rocket. In single stage rocket, let me derive expression for velocity. Derivation of expression for velocity of a single stage rocket. Of a single stage rocket. Okay, now here I will be deriving the expression for velocity of a single stage rocket. So we will be deriving what will be the velocity of single stage rockets, right? So we will be deriving equation for of rocket now here. Okay, let me begin now here. Let me consider a rocket like this. Okay, so let us understand it diagrammatically. So this is a rocket, right, whose mass is m and it is moving with the velocity v, right? So whose mass is m, it is moving with velocity v at time t. So v is the velocity at a time t, and what is its mass now here? M. After some time, it loses the mass. We know that when it loses the mass, the rocket begins to move much more faster now here, right? So it loses the mass. How much mass it loses now here? Let me take it as dm. And if it loses mass dm, it moves with much more faster velocity v plus dv, right? So that too at time, right, after time t plus dt. Okay, after time dt, it lost mass dm, right, and velocity increases by v plus dv. Now what is the mass of the rocket now? M minus dm, because it lost mass dm, right? Okay, so this mass is lost in this direction and it also has some velocity, and the velocity of the exhaust mass now here, let me call it as ve, right? So this is ve with respect to rocket. With respect to rocket, ve is the velocity of the exhaust mass now here. And if you see with respect to ground, right, so its velocity is v in this direction and it is losing mass in the downward direction, right? So the relative velocity, right, if I am considering now here v plus ve, right, v is in this direction and v is in the opposite direction, so we may consider it as plus, right? So its velocity is v plus ve with respect to what we say here, ground. If you see with respect to rocket, okay, what is the velocity of the exhaust mass now here? That is v. But if you see the same concept with respect to ground, what is its velocity? V plus ve, right? Okay, so its velocity again with respect to ground, we are speaking with respect to ground here, right? So as the rocket is moving, it is losing the mass now here, right? So as it is losing mass while it is moving, so we can consider it into two frames, one rocket frame, another one is ground frame. The velocity with respect to moving rocket is ve, right? Velocity of the exhaust mass with respect to moving rocket is v, and velocity of the exhaust mass with respect to ground is v plus ve, right? So you need to understand this. Let me write. Consider a rocket of mass. What is its mass now here? M, right? Mass m, moving with the velocity. What is the velocity? It is moving with velocity v. Do remember, at the time, I am speaking at the time t now here, right? At the time t, what is its mass? M, and it is moving with velocity v. right? Okay, consider a rocket of mass m moving with velocity v at a time t, right? Okay, just I wrote about the first diagram. Now let me go with the second diagram. At after time dt, what happens? Let us check it out. After time, what we say here? Dt, right? After time dt. So this is the time t. After time dt, the time will be t plus dt, right? After time dt, after some time, right? Let the mass expelled be dm now here, right? Okay, now let us consider after time dt, let the mass ejected, right, or expelled be dm. After time dt, let the mass ejected be dm. Let the mass ejected be dm. So what is its velocity? With velocity ve, right? That too with respect to moving rockets. With respect to moving rockets. Okay, so what is its velocity v? Shall I write like this? This is with respect to ground. Do remember, the velocity of rocket is v with respect to ground, but the velocity of the ejected mass is ve, that too with respect to moving rocket. If you consider it with respect to ground, it will be v plus ve now here, right? Okay, after time dt, let the mass ejected be dm with velocity v with respect to moving rockets, right? Now what happens here? The mass is decreased by m minus dm, right? The mass of rockets is decreased by, it is the mass of the rocket is decreased to m minus dm. Let me write like this, is decreased to m minus dm, and velocity increases to, what is the velocity increase now here? That is v plus dv. Do you understand this? Right, simple, right? There is a rocket whose mass is m and velocity is v at time t. After time dt, it is spitting something, right? It is ejecting the mass in the form of gases now here, right? Okay, do you understand? This is a rocket which consists of fuel, right? And when it burns, it loses some mass, right? What is that mass now here? Dm, right? When it loses the mass, it gains momentum in the opposite direction, right? The velocity increases. What is the increase in velocity? v plus dv. What is the loss in mass now here? Dm. So what is the present mass now here? m minus the dm, right? And ditto happens after time dt now here. That itself I have written here, right? Okay, do remember, this is what actually how the rocket works now here, right? Okay, now let me go with the mathematical equations now here, right? Let us check it out how actually the law of conservation of momentum works here. Now let me take first initial momentum and final momentum. Let me take now here what is the initial momentum of rocket is. Initial momentum of rockets, right? What is the initial momentum? Let me take this initial momentum. Let me call it as pi, that is initial momentum. Okay, what is the initial momentum? Momentum is mass into velocity, right? Mass is m, velocity is v, and it is moving in the upward direction. Let me call it as m into what we say here, v. This is initial momentum of rocket. Next, let me go with what is the final momentum of rockets, right? Let me go with final momentum of rockets. So what is the final momentum? Let me take pf. The final momentum of rockets, let me consider like this. There are two things which are moving, right? Some mass is moving upward and some mass is moving downward. Let me consider both now here. What is the mass of the rocket now? m minus dm. This is the mass. What is its velocity? It is moving with velocity v plus dv, right? I consider this. Now let me consider this also, right? Because it is also moving now, right? Plus, what is the mass which is coming outside? dm. And what is its velocity? The velocity is v plus v, right? We are considering with respect to ground because everything is considered with respect to ground. That is why we need to consider with respect to ground, and the velocity is v plus ve in here, right? So this is the final momentum of the rockets. Now, let us calculate what is the change in momentum. Right? What is the change? Let us check it out. The change in momentum, it can be calculated like this. What is change in momentum? That is Pf minus Pi. Now, what is Pf? Let us check it out. What is Pf? We have m minus dm v plus dv into, right, plus dm into the bracket v plus v. So this is a final momentum. What is the initial momentum? We have, what is the initial momentum? mv. Let me write like this, right? Now let me simplify this. So what do we get? So first I multiply m with this, m into v plus m into dv. I multiplied m with this term. Next, with this term, minus v into dm. Again, what do you get now here? Minus dm into dv, right? Simplifying this term, I got this, right? Okay, what do I have here? Plus dm into v, what do you get? v into dm plus ve into, what shall I write now here? dm. So what is remaining there? Minus mv. Okay, now let us check it out. If there is any term which get cancels out now here, right? Okay, yes, there are some terms which get cancels. So mv cancels with mv. Then is any other term? Yes, we have here vdm, vdm. So this also get cancelled. So what is remaining? Let me write here. That is m dv, right? There minus dm into dv here plus ve into what we say here? dm. But dm and dv are too small so that it can be neglected. So this can be neglected. So what do we get now here? m into dv plus ve into dm. Why? Because dm and dv both are what we say here? Small, right? As dm and dv both are small, this term can be neglected, right? The product of small term, again it will be much more smaller now here, right? So let me neglect this term because both are small. So we got m dv plus ve dm. What is this? This is nothing but change in momentum. Let me write change in momentum as dp, right? dp is equal to m dv plus ve into dm. Now, after getting change in momentum, let me go with rate of change of momentum, because we know from Newton's second law, force is directly proportional to rate of change of momentum. So let me take that now, right? We got change in momentum. Then now let me go with rate of change in momentum. So what is the rate of change in momentum with respect to time now, right? The rate of change in momentum. So let me write, that is dp divided by dt is equal to m dv divided by dt with respect to time here, right? Plus ve dm divided by dt. So this is change in momentum. This is a rate of change in momentum. So dp by dt we got like this. Now we can link this to force, right? We know that according to Newton's second law, right? According to Newton's second law, I will be writing what is the expression for external force. External force which acts on the rocket, right? Okay, let me write now here. What is the external force which is acting on the rocket now? Let me take now here. So what is the external force? Let me write it as F external, that is equal to, right? We know that from Newton's second law it is equal to dp divided by dt, right? But we have what is dp by dt? Let me substitute there. So what do I get here? That is equal to m into dv upon dt plus ve dm upon dt. This is rate of change in momentum. Let me substitute there, right? Okay. We know that as the rocket, we know this is a rocket, it expels some mass and moves with a greater velocity. Let me call it as v plus dv. What is the loss of mass now here? M minus dm, right? Now if it is moving like this, this force, let me call it as upward thrust now here, right? Okay, upward thrust of rocket is opposed by external force of gravitation, right? There is an external force of gravitation. The gravitational force is pulling down. This gravitation force is nothing but weight of the rocket, right? Okay, upward thrust of rocket is opposed by external force of gravitation, which is weight of the rocket, right? It is nothing but Fe is equal to mass of the rocket into acceleration due to gravity, right? Okay, if I am speaking the mass is m, acceleration due to gravity, let me take it as g, it is nothing but weight of the rocket. But we are calculating the velocity neglecting the weight of the rocket. Okay, let me write down, neglecting weight of the rocket. If you neglect weight of the rocket, right, what happens? Let us check it out now here, right? Do you remember? Upward thrust of rocket is opposed by the external force of gravitation, which is nothing but weight of the rocket, right? We are deriving the velocity of the rocket neglecting its weight, right? If you neglect the weight, this is nothing but what? mg, this is nothing but weight of the rocket, right? If you neglect it, let me write it 0. So what is remaining here? M dv upon dt plus ve dm upon dt. This is the expression we get after neglecting the weight of the rocket. Now, I need expression for velocity. Let me move ahead now here. I need the expression for velocity. Where is velocity? So we have the velocity is here, right? So let me find what is the velocity now here, right? Let me take m dv divided by dt. Let me take like this, right? So this term will come this side. So what do you get now here? Minus ve, what shall I write now here? Dm divided by dt, right? So I want what is the velocity, right? So I need to integrate it. So this can be written as like this, m into dv, dt dt. Let me cancel it out now here. So what do I get now here? Minus ve into dm. Why did I do like this? Because I want to integrate it now here, right? Okay, now let me integrate m, integration now. Let me take the starting velocity is v naught now here and the final velocity is v. Let me take it as dv, right? So this is the initial velocity, right? Okay, let me take this, may be considered as 0 also when the rocket is at rest now here, right? So this is the initial velocity and this is the final velocity. Let me take like this, that is equal to minus v integration of m naught to m, what we say here, dm, right? So m naught to m dm now here, right? Okay, what I will be doing before integrating, right? Let me bring m to this side because we have dm here, right? Okay, let me take like this, dm is equal to minus ve dm divided by m. Let me take this, now let me integrate it. So what do you get? Integration of v naught to v, let me take it as dv, that is equal to minus v integration of m naught to m. This is initial mass of the rocket, this is the final mass of the rocket. What do you get? 1 by m, that is dm, right? 1 by m, that is dm. Now integrate, we have integration of 1 dv is v, right? Here let me write v naught and here v, that is equal to minus v integration of 1 by m, we know it is log m to the base e now here, right? Okay, so let me take now here m naught to m, right? So this is the log m to the base e, m naught m. Okay, now let me simplify to get the velocity of the rocket now here. Now what do I get? Let me write here. This can be written as, this is first v minus, what shall I write now here? V naught. V minus V naught. Okay, first let me put upper limit minus lower limit now here, right? Okay, that is equal to minus VE. This is integration of 1 by m is log m. We got this. Okay, first let me substitute m now here. What do I get? Log m minus log of m naught. Let me write like this, right? Okay. Now let me simplify. V minus V naught is equal to minus V log of m divided by m naught. Right? Okay. There is minus here. So what I will be doing? I will be removing this minus. Means if I remove this minus, you can make it reciprocal m naught divided by m. Right? It can be sent to the power here minus 1. If I get minus 1, again you can change the numerator and denominator. We can make a reciprocal of this here, right? So we will be getting with V log of m naught divided by m. Now what is the velocity? V is equal to, let me send this to this side, V naught plus VE log of m naught divided by m, and this is the velocity. Right? So this is the velocity of the single stage rocket. So what is the velocity? V is equal to V naught plus V log of m naught divided by m. Right? So what is V naught? Initial velocity. Right? If you consider it as a rest, okay, it will become 0 now here. Right? This is initial velocity. What is VE? This is the velocity of the ejected mass with respect to moving rocket. Right? So log of m naught divided by m. What is m naught? M naught is the initial mass, right? M is mass at time t here, right? So if I am considering this, V is equal to V naught. This is the velocity of single stage rocket. V is equal to V naught plus VE log of m naught divided by m. This is the velocity of the rocket at time t when the total mass is m. Next, we shall see how we can increase the velocity of the rocket, right? So we need to increase the velocity such that it must be greater than the escape velocity, right? So that what we can do to increase the higher velocity, right? Okay, to obtain a high velocity, of the rocket, what we can do, let us check it out. To obtain high velocity, this is the formula for velocity, and what we can do to obtain the higher velocity, right? This is initial velocity of the rocket. If it is at rest, let me take it as 0 now here, right? So again, it depends upon VE. How it depends? It depends directly now here, right? So the first way to increase the velocity of the rocket is increasing the speed of what we say now here, emitted, right? So ejected mass, right? So the first way is to increase the velocity, of ejected mass, right? So we need to increase the velocity of the ejected mass, right? If you increase, means the engine of the rocket must be so strong that it ejects with a high velocity, right? If it ejects high, okay, the rocket will move with the higher velocities, right? Okay, do remember to increase the velocity of the ejected mass, right? So to obtain high velocity, the first way is to increase the velocity of the ejected mass, and you can increase by the second way. How to increase? We have this ratio m naught divided by m, right? This should be high. The ratio of m naught divided by m should be high. Its meaning is that m should be lesser than what we say here, m naught, right? So let me call now here, that is final mass of the velocity, final mass of the rocket, is less than, must be less than now here, right? Final mass of the rocket must be less than initial mass. Let me take like this. Okay, final mass of the rocket must be less than initial mass, right? So this is final mass and this is initial mass. Means as the rocket moves, it must lose the mass and it must lose more mass, right? If it loses more mass, it goes with a higher velocity. Means there are two ways to increase the speed of the rocket. One, by increasing the speed of the emitted mass now here, ejected mass now here, right? The second way, the final mass of the rocket must be very much less compared to that of initial mass of the rocket. So if these 2 points fulfills, then you can move the rocket with a higher velocity. Okay, now let me speak practically what happens now here, right? Let me speak practically Practically, let me take, what is the initial velocity of the rocket? Let me take it as 0, right? Let me consider the rocket is kept now here, right? What is its initial velocity? 0. What is the velocity of the ejected mass? Means that engine ejects the mass. The practical value of the velocity of the ejected mass is 2 kilometer, right? So it is 2 kilometer per second, right? So if I am speaking with what is the ejected mass? The ejected mass is 2 kilometer per second, right? It is a maximum. You cannot, the engine cannot eject faster than this, right? Right? What is the velocity of the ejected mass here? That is 2 kilometer per second, and the value of m0 by m, practical value, is 10 here, right? It cannot be what we say here greater than 10 here, right? So practically it is 10. Let me substitute and calculate. What do I get? V is equal to V0. In place of V0, let me take it as 0 plus what is V? 2. Let me take log. What is its value here? 10 to the base e. Okay. What do I get? Right. V is equal to 2 log 10 to the base e. If you calculate this, you will be getting with 4.6 kilometer per second, right? So this is, do remember, it is not a base 10, it is base e now here, right? So if you calculate this, you will be getting with 4.6 kilometer per second. Means the maximum, the speed of the rocket, right? Okay, if you consider this situation, the speed is 4.6 kilometer per second. What is the escape velocity of Earth? What is the escape velocity of Earth? The escape velocity of Earth is 11.2 kilometer per second, right? If you want to escape from the gravitational pull of the Earth, the speed must be minimum of 11.2 kilometers per second. But what is the velocity of a single stage rocket? It is 4.6, right? If you want to make the satellite to move in a orbit, we know that orbital velocity is also nearly about 8 kilometers per second here, right? But it is even less than that, right? The velocity of the single stage rocket is less than both escape velocity as well as even it is less than the orbital velocity. So this is the reason why we cannot use single stage rocket. The problem with single stage rocket is it cannot move greater than the escape velocity and the orbital velocity, right? The velocity of the single stage rocket is less than the escape velocity, right? To increase the velocity, we are moving with multiple stage rockets, right? So this is the reason why we are not choosing single stage rockets, right? So single stage rocket do not work because the speed is less than the escape velocity. That is the reason why we go with the multiple stage rockets, right? So this was the session about a single stage rocket and what is its limitation. And in the next session, we will be moving with we will be dealing with multiple stage rocket. So this was all about a single stage rocket. Thank you.